Okay, welcome everybody. This is my second talk of this conference, so I'm already exhausted. As I said, this is a very intensive presentation, and I have like 90 slides. So there is no way we're going to get through all of this. So instead of 7 things every programmer should know, this is really 7 categories of things that everyone should know. And I guarantee that even if I only get through 3 categories, you'll have all learned more than 7 things. So maybe we have to cheat a little. So those of you who came to my talk earlier today will have heard me talk about the exponential growth in programming as something people do. And that is no more true than for Python at the moment. Look at the growth of Python from this blog post from Stack Overflow earlier this year. It literally is exponential, it's huge, and it's outpacing almost everything else. So Python is hugely popular. It's used in so many different domains. So data science, building software that's written in C++, configuring stuff in the cloud, building websites. Python is used for all kinds of different domains, which I think is what's behind this growth. And this growth is just incredible. It's gone up by a factor of 2 in 5 years. In fact, you can use the function on the right of the screen to figure out how many million Python developers there are in any given year. This is 20% annual growth. Back in 2012, there were 3 million Python developers estimated to be in the world, and already there are more than 7 million. What this exponential growth means is that most Python developers have relatively little experience, just because the influx of new people is so high. And in any situation where you have exponential growth, the newcomers tend to rapidly outnumber the oldsters like me. I've been programming in Python since 1999. So because of that, this talk is unashamedly focused on what I consider to be pretty basic, fundamental things that every Python programmer should know, okay? Because most people just don't have that much experience. When I go to tech conferences, I'm always surprised at the incredible sophisticated things people are presenting, and sometimes the mismatch between that and the skills that people have already managed to build. So this is basic, straightforward stuff. So 7 things. Number 1, know when code is executed. You might think this is simple. You might think code is executed when it's called, but it's more complicated than that. So here's some code. I didn't write this. This is part of the Apache Kafka binding for Python, written by people who really know how to code. Apache Kafka is a very serious piece of software. So which code is executed when we import this module? Everything you can see on this screen with a yellow background is executed when we import this module. There's a compiler directive at the top that changes the behavior of the language. There's a whole load of imports. They're all executed when this module is imported. There's a global attribute called log being created and a method call being made to initialize that attribute when the module is imported. There's a class definition. Class definition is something that happens at runtime in Python. Those of you who worked in other languages like C++, classes are a static thing. They don't even exist at runtime. We have some class attributes being created. These are like static attributes if you're used to C++. Static class attributes. These are being created when the module is imported. And the method definition of init function is being executed. The body of the method is not executed, of course, but it is parsed. But the definition, that def statement, is executed. And as we go through this pretty substantial piece of Python code, I've highlighted all the bits in yellow which are executed when the module is imported. All the method definitions are executed. There's lots and lots of method definitions in this file. There's a decorator here, a property decorator, that is also executed. Does some work to wrap up that function, topics, in a thing called a descriptor. That's happening when we import the module for the first time. Lots and lots and lots of method definitions here, all executed. Some more here. Did you see the obvious bugs in this code as it was flying by in those yellow bits? Probably not, but maybe some of the experienced Python programmers will have spotted them. There are, of course, two types of Python developers: those who didn't spot the bugs and those who did. So where are they? Let's zoom back up. Here they are. There are 3 of them right here. Bear in mind, this is the Apache Kafka binding, and it's probably in production in hundreds of important places. Can you see them now? So those of you who've done a bit of Python probably understand what's going on here. And it's potentially very serious. Because these lines in yellow are executed only once when the module is first imported, these empty lists are constructed only once. They're constructed exactly once when the module is first imported. And lists, with the square brackets, are mutable data structures. And so any modifications to that list will persist across calls to the same function. Okay? So you've made your function have some persistent state beyond the life of each function call. So this really innocuous-looking thing with this default argument of a list is actually potentially very dangerous. Let's demonstrate that with a simpler example. This is my very simple version of send request. It accepts some payload objects. And the actual payloads it prints out are going to include a first item, which is the number of items in the payload list, including the integer itself. So let's see how this works. If I send 3 items, I get a list with 4 items in it, and the initial 4 there is the total length of the list. Very straightforward little function, this. If I pass 2 things in, I get the result I would expect, a list with a total of 3 items, including the count in the first item. If I send an empty list in, it still works. I get a list with 1 item containing a count of 1. So you might think that calling it with the empty list is equivalent to what we get in the default case. Let's see. So passing the empty list in works multiple times. If we rely on the default argument, though, it still appears to work. But the next time we call this, we've carried over some state from the previous invocation of the function. And on, and on, and on. And this list will only ever grow each time we call the function. So this is definitely something you need to know about Python programming, is that when you are dealing with default empty collections, you really don't want to be using a multiple collection in case that state is carried over, because that collection is only initialized once per run of your whole program. How do we deal with this? Well, we could use an immutable collection. The parentheses here are an empty tuple. Tuples are immutable, so we've made ourselves immune to that particular problem. And this version of the function has much better behavior. We now don't suffer from the problem of accumulating state across invocations of the function. This particular solution of using an immutable tuple, I hardly ever see it, and I've read that people feel it's inappropriate because now it looks like you have to send a tuple into the function rather than a list. So it's not very popular, even though it works. Much more popular and better is to use a Sentinel value, none, and then detect whether the default value Sentinel has been relied upon. And if it is, then create an empty list within the function. You can see here I'm doing payloads, will be payloads if payloads is not none, otherwise create a new list. And of course that will happen afresh on every invocation of that function. So there's no way for us to carry state across calls to the same function. So that's the much more widespread solution to this problem, and something you should know about. As you can see on the right, this works as expected now when we rely on the default. You might see a shortcut for this. I don't see this so often these days, and I wouldn't recommend writing the code this way, but it is maybe something you need to know how to read. You can see here I'm using payloads equals payload or the empty list. And this relies on a quirk of the way the logical operators work in Python. It reads quite nicely in English, but it is relying on a kind of oddity of Python, which we will return to later. But this has the same behavior. Okay, number 2. Well, in that previous version, we relied on a Sentinel object non in order to flag up the use of, or the reliance on the default argument. So in this section, I'm going to expand on the use of Sentinel objects like non and give you some alternatives. Some very important techniques here. So on the left, you don't have to read all this code. You just have to understand what it does. We have a function called batched, which will take any iterable series and collect it up into batch sizes that we give it. So let me give you an example so you can see how that works. We'll import batched. Well, I'll make a list of numbers. These are the even numbers up to 20. There we are, using a range. So that's our input data. And I'm going to pass that input data to my batch function with a batch size of 3. And we get a list of lists as the result with a batch size of 3. But of course, because my input data isn't a multiple of 3 long, we have a partial batch at the end. Okay? So you'll notice that the definition on the left has a padding argument, which is defaulted to none. So let's try to do batching with padding. So now I'd like to pad any partial batches with 0, because I don't like the fact that all of my batches are not the same length. So when we run this, you'll see that the final group there has the 2 zeros padding it, so it has a length of 3. Now I'd like to pad it with none instead. This is a reasonable thing to do. What happens when I pad with none? It doesn't work. Why can't I pad with none? Because I've used none as the Sentinel value to detect whether the default argument is in play. So now I'm doing something that in item 1 I recommended you do, and now we've fallen flat on our face. It doesn't work. So what we need is something like none that isn't none. A none is just a singleton object in Python. There is only ever one instance of none in the whole program. So we can play the same trick. We can make another object of which there is only ever one in the same program, and it's very, very easy to do. If you look at the top left on the definition, I'm now creating an object called unset. I've put it in capitals because it's a constant. I'm just going to create an object. That object doesn't have to have any particular type. I only care that it's a distinct object that nobody else has. And I'm going to call it unset. Okay? Now, in my definition of the code, near the bottom, you can see where I say, if padding is not none, 3 lines up from the bottom. I can now change that. Or I can change my default argument first, so as padding defaults to unset. And now I can say, if padding is not unset. And nobody else really knows about this unset variable or how to get hold of it. So there's no legitimate reason to want to actually pass unset into this function as the padding object. So now, because I'm not using none, with the new version of the function, create some numbers again, do the batching, and now I can do padding with none, and I get padding with none. So sometimes you'll see people just creating these objects of type object. We don't really care about the details of that object at all. We just want a unique object in the program. And quite often that's done at global scope, out in the with no indent in the module. So that's a useful technique to know if you need a default, but you need something that's completely out of the domain of the values you would normally use. It also means you can give your default a nice name rather than having it called none. So unset fits in this case. There are other cases where other names might fit. Okay, very important thing about Python is to know how scopes and namespaces relate. These ideas often get confused in people's minds, and they use these terms interchangeably, but they have very specific meaning. Yeah?
Are you talking Python 3, or does this apply to...
I only ever talk Python 3, James.
Sorry.
Yeah, Python 3. So, this is the Zen of Python. Who here is a Python programmer? Okay, who's familiar with the Zen of Python? Okay, everyone who's a Python programmer. You can get the Zen of Python in Python just by typing import this. It's very nice to be working in a language that comes with built-in poetry. I'm not going to read the whole language, the whole poem to you. I want to highlight the last one, though, which is that namespaces are one honking great idea. Let's do more of those. Let's get to grips with what namespaces are and how that relates to scope. So a namespace in Python is a collection that binds the names of objects to the actual objects themselves. Whereas the scope is the region of the program in which a particular name binding applies. Okay, so it's a region of the source code. Now, I often say that everything in Python is an object. It's almost, which is true, it's almost true that everything in Python is a dictionary as well. Almost everything in Python is a dictionary. So namespaces in Python are also dictionaries behind the scenes. So on the left, you'll see me typing some code, and on the right, you'll see the actual namespace. It comes with a bunch of built-in stuff by default, but if I do x equals 42, what that actually does in Python is create an entry in the namespace dictionary, x mapping to 42. Some things we do in Python don't modify the keys, they only modify the values. There are lots of ways of manipulating the namespace. Here I'm importing a function or a class into the namespace. Here I'm defining a function. That puts a function into the namespace, mapping the name of the function to the actual code of the function. I define a class. That adds another entry in the namespace, mapping the name of the class to the code of the class. I can remove things from the namespace with del. I can even dig around in Python using some introspection and dig out the actual namespace object as a dictionary and manipulate it directly. So this is really what, when you do assignment, this is what Python is really doing behind the scenes, is it's directly manipulating the dictionary. So namespaces and the dictionaries that they're implemented as are everywhere in Python. Hard to avoid. So when is a namespace created in Python? Well, it's created every time you import a module. That module has its own namespace. That's called the global namespace in Python. Every time you execute a function, a namespace is created. That is the local namespace to that function. Every time we define a class or run a class definition, a namespace is created for the class. And every time we instantiate a class by creating an object, a namespace is created for the instance. So notice that the class namespace and the instance namespace are distinct things. And this leads to some confusion and some idiosyncratic behavior in Python. So lots of people, when they're teaching namespaces, show them as this kind of nested arrangement of namespaces, the local namespace to a function, the global namespace to a module, and a built-in namespace, which contains built-in types and functions, things like list and tuple and string. And I've been guilty of presenting nested namespaces in this way. But I think it leads to some confusion, because people see the nesting of the namespaces here, and they conflate that, they confuse that with the indentation of the code that you can see on the right-hand side here. And these are quite different things. So in the code on the right, I create a global variable, I create a class, I have a class attribute, and then I define a method where I try to print those things with a local variable in it, which I try to print out. When we run this, although it looks like it should just work, we are met with a surprise. And the surprise is that the class attribute can't be located. It looks quite reasonable that these three print statements, one of them can find the global variable well outside, the one in blue can find the local variable inside the function, but the red one fails in this kind of intermediate space. What's going on there? Well, to understand this, we need to look at how scopes work and how name lookup works in these different dictionaries, these different namespace dictionaries. And the way it works in Python is that the namespaces are essentially chained together by two special attributes. One is the module attribute. In Python, by the way, when we have these underscore, underscore, module, underscore, underscore, that would double the length of this presentation if I had to say that every time. So we say dunder, which is short for double underscore. So that is dunder module and dunder built-ins, right? So you need to, you're all smiling because I sound stupid, but when you hang out only with other Python programmers, it's just okay. So dunder module, dunder built-ins, and the lookup mechanism follows the dunder module references to get through nested namespaces. The problem is that classes aren't on this lookup data structure. So you can see here at the bottom in blue, we have a local method. It has a dunder module attribute, which the lookup will follow, but it will follow it to the global namespace, bypassing the class namespace, which is why the lookup of that class attribute fails. If you want to get into the class namespace, the bottom center in red there, then you need to explicitly find something that is on the lookup path and navigate back down to it. So to fix our example here, here's the original example which failed. To fix this, we need to find something that is on the in the global namespace, which in this case is my class. The class is declared in the module. So to get this to work, we need to put myClass attribute in there. Now you might think this is a design flaw in the language, and I wouldn't disagree with you. But that's just how it is, and you need to know about it. And it's unlikely ever to change. So it's important to understand the LEGB lookup rule, local, enclosing, which I haven't talked about, global, and built-ins. The most important thing about how you spell LEGB is that there is no C in it for class. Okay? So if you want to find something that's in a class, you have to find something that is at one of these levels and then navigate back down to the class. Okay, number 4. No trade-offs for number types. This is one of my favorite topics. I worked for many years in areas with lots of numerical computing. And I kind of have this view of choosing the right number type in any system where the answer is actually important, which is that you really need to know what you're doing. And it's traditional at this point for the speaker to say, well, you should just go and read that document, what every computer scientist should know about floating point arithmetic. The problem is nobody ever does. Very few people have actually read it, and fewer have really deeply understood it, and even fewer have really deeply understood what the implications of it are when we're actually writing code. So I'm not going to recommend that you read that. I'm just going to show you some practical examples and explain some differences. So the built-in number types in Python are int, which is an unlimited precision signed integer in Python 3. It's a very good reason for using Python 3. Your integers will not overflow. You won't hit any problems until your 16 gigabyte memory is full of an integer. You can do some really crazy math with that. We have a float. And Python's float really is exactly the same thing as a C double, right? That's actually how it's implemented. So Python's view of float is whatever your C compiler's opinion on double is. And we have complex, which is a pair of floats. We also have two other number types in the standard library. We have decimal And we have fractions for representing rational numbers. And these, I rarely see these things used. Particularly, there are cases where people use decimal. I very rarely see fraction used in practice. So I'm sure everybody here who's ever done any math with a computer is familiar with the failure modes of float. And people get very upset about this kind of thing. The fact that we can't even do very simple operations that even a 7-year-old could probably do with a computer and get the right answer. And we throw up our hands and say, oh, well, numbers are broken, computers are hopeless. And of course, the reason this is happening is that float numbers are inherently binary. They are base 2, and we cannot represent either 0.8 or 0.7 as a base 2 fraction in finite precision. You can see the bit patterns of these two numbers here. You can see the recurring pattern, and imagine how that needs to carry on to infinity in order for us to represent these numbers. So what people do is they go to Stack Overflow, and they get some advice. I didn't put it in here for fear of embarrassing the person who wrote the answer who wrote it, but the advice goes something like this, is, well, if you have problems with float, you should just use decimal, because decimal avoids all these problems. Yay, decimal. And it appears that we can do things with decimal, sometimes even with numbers that we can't nicely represent in decimal. So here I'm subtracting 3/3 from 1, which is 0, right? You might be surprised that that works in decimal, but it does. But we've been lucky. All I need to do is put 2 extra parentheses in this expression to force the order of operation to be slightly different, and it stops working. And in fact, decimal is really no better than float in this respect. It's just a different set of trade-offs. Oh goodness, numbers are broken. And people have this idea that decimal is somehow some magical number type that works in a completely different way from float, and it doesn't. Float is a floating point representation. Well, decimal is also a floating point representation. Float is IEEE 754. Decimal is also IEEE 754, but base 10. The IEEE 754 standard these days doesn't just talk about base 2 numbers. The base is a parameter you can plug into your number type. So decimals are included. The main difference between these two things is that one is base 2 and one is base 10. One of them is built in, and one of them is in the standard library. The float is almost certainly hardware accelerated if you have a floating point unit on whatever processor you're using. Decimal will never be hardware accelerated, even if you have decimal hardware like you would have on an IBM Power CPU. And float is very fast, and decimal is about 2 to 3 times slower than float. So decimal isn't the way out of many of these problems. So let's look at a computational geometry problem. I worked a lot in oil and gas a few years ago, dealing with lots of geometric problems. So I like computational geometry problems. And I'm going to show you what's called a collinearity predicate in the code for that. So the question we're trying to answer is the point P above the line, on the line, or below the line? Well, if we draw a triangle between P, Q, and R, when P is above the line, we get a counterclockwise triangle. When it's on the line, well, we don't really get a triangle. And when it's below the line, we get a clockwise triangle. So that's neat, isn't it? And it turns out that by computing the signed area of that rectangle, of that triangle, you can figure out whether the point is above the line, on the line, or below the line. And we do that by figuring out the sign of the determinants. The math isn't important here. So let's do the sign of the determinant in Python. We need a signed function, which distressingly Python doesn't come with, so we have to write one. And we need the determinant function there. So we have an orientation function. We can give it P, Q, and R as 3 pairs of numbers, as tuples, and it's going to return -1, +1, or 0. Really nice function, very simple. Even if you don't understand the math, you can understand how to use it. And here's a demonstration of it working. On the top of the right, we have 3 points in a line, 0, 0, 4, 4, 8, 8, and we get 0. Very nice. Whereas 0, 0, 4, 4, 4, 0 gives us -1, because we're below the line. Great. However, we're very diligent, and we like to test our functions. So let's see how this function behaves very close to the line. And I mean very close to the line. Right? So let's actually use the computer to calculate every possible float in a sequence near to the line. So we can do that. And you'll see here that we're getting a series of 1s above the line. You can see the second coordinate there. They're all 0.5, 0, 0, 0, and some number, so we're above the line. And we're getting 1 for above the line. That's great. And as we get closer to the line, then we begin to get zeros. So this function thinks all of those points are on the line, but you know that that can't be true. Okay? And then you might think that the next thing that's going to happen is that we're going to enter a region where the points are below the line. I'm sorry, now we're above the line again. If we go a little further, now we're back on the line. The one in green there is the only point where we are actually on the line, which thankfully it does get the right answer for. But in the region below the line, we're still on the line. Now we're below the line with the -1 there, except we're back on the line again. And now finally, we're actually below the line. So there's this really complex region around the line where this function gives really pathological behavior. Really terrible. And of course, with different query points, you can get inconsistent results. You can get 2 points where you know one of them is above the other, but the ordering given by this function is completely incorrect. So how to fix it? Well, let's go back to our code. Turns out the fix is incredibly simple here. All we need to do is convert our floating point coordinates into rational number coordinates using the fraction type. That's the only change we need to make. I'm just replacing P, Q, and R with their equivalents represented as fractions, rational numbers. Now when we do this, we get a beautiful answer. We're consistently above the line, we're on the line at exactly 1 point, and then we're consistently below the line. Lovely. We can even map in 2 dimensions a region around a very small rectangle around the line. And I love the picture that's coming next. So the points in white are above the line, the points in gray are on the line, and the points in black are below the line. Okay? So it's a very vivid graphical demonstration of how floating point numbers behave and why you need to test these things in the regions that you're using them. You see, fraction gives an exact result, but there's always a trade-off. It's 45 times slower. Right? So you need to decide whether that's an acceptable trade-off. You might think, you see lots of software that using floats that adds some kind of tolerance value. The problem with this tolerance approach is it just pushes this fringing effect out, and you end up with a very thick line with these horrible fringes on the edge of it. So it only helps to a certain extent. Okay, you need to know some quirks of the language in Python. Python is imperfect, and anyone who's used a language for long enough learns how imperfect their language is and yearns for something better. But what's the saying about, there are languages people use and the ones they complain about? So, let's look at some quirks. A is 42. That's a floating point type because it's got the 0.0 in there. A is integer. True. That seems like a reasonable answer, doesn't it? B is 42 as well. B is integer, isn't even supported. So you can ask floats if they're integers, but you can't ask ints if they're integers. So much for polymorphism and duck typing. Tuple is a subclass of a thing called sequence in Python. A sequence is basically anything we can index into with an integer, like a list, or a tuple. String is also a sequence. Does the tuple 1, 2, 3 exist in the sequence 1, 2, 3, 4, 5? No, I think this is the right answer, because the tuple on the right contains integers, and I'm saying, is this tuple in a list of integers? And no, it isn't. None of those elements are tuples. I think this is the right answer. What do you think it's going to do with strings, which is also a sequence? Oh dear. So the behavior of Python can be quite surprising sometimes. And this makes it very difficult to, say, write functions which work generically on both a tuple and a string, or a list and a string. Because string has this non-intuitive behavior where the in operator has been overridden to do substring test rather than a membership test. I don't want to turn you off Python, by the way. I love it. It's the language I keep coming back to. I can program in half a dozen different languages, or if not more, but Python is the one I keep coming back to. But I do want you to be aware of the traps. Here's another one. A is a list. Lists are mutable. B is a tuple. Tuples are immutable. Is A equal to B? No. That's fine. C is a set, which is mutable. D is a frozen set, which is immutable. Symmetry tells me that this should return false, but unfortunately, it returns true. Okay, so I think some decisions were made that were not necessarily fully thought through, and we just have to live with them now for the sake of backwards compatibility. Designing languages is really hard. Here's my favorite quirk. So when I'm teaching Python, I've just been teaching a 2-day class on basic Python, and I try to encourage people to use keyword arguments when they're calling functions which have more than 1 or 2 arguments, because then we don't have to remember at the call site what the arguments are for. Seems like good advice, right? So let's do that with range. Oh dear. Turns out that range, which is a built-in function, does not support keyword arguments at all, which is really disappointing, because I can never remember exactly which is which. So as well as knowing quirks, you need to know some idioms. I'll rattle through these quite quickly so I don't run out of time. Here are some unpacking idioms. I know what I like. A is no and B is like. This is the way to swap things in Python. Use tuple unpacking. Create a tuple on the right-hand side, unpack it on the left-hand side with the arguments reversed. I like what I know. So that's the idiomatic swap Python without a temporary. You can use the underscore variable in the Python REPL in the console to get hold of the last result. So text is now equal to I like what I know. Let's split that sentence into words. When you have the urge to iterate using a range and an index in Python, you need to resist it very strongly. It's not how we do things in Python. Python is not C++. If you want an index and the item, you should use the enumerate function, which will return a tuple of index word, index word, index word as you go through. And you can use tuple unpacking to unpack those into 2 variables, index and word here. In modern Python, we have some really quite clever extended unpacking. So I can unpack the first item into one variable and all the other items as a list into the other variable. So I can get head and tail like this. It's very nice. That's quite new in Python. And I can use the same trick to do things like getting hold of the first and last line of a file and discarding all the other lines. So here I'm opening my dictionary on my Mac, reading the whole file with read lines, and I only care about the first and last items, and I can ditch all the ones in the middle. So the first word in the dictionary is A. The last word is, well, zizogeton, whatever that means. Chain comparisons in Python. If you're doing C++ or C, you might be tempted to write a comparison like this. That will work in Python. It's much more Pythonic to write it like this, like you would do it in math. Python's very nice about supporting this syntax. The logical operators in Python work in quite a strange way. They return the first argument that allows the decision to be made, right? So 6 or 7, we can decide that with 6. We don't need to know that. We don't need to evaluate the 7 to know that 6 is true, right? Whereas with the second example, we need to look at the 7 to check whether the whole expression is true, and works in a similar way. So you saw me use this earlier to detect whether an argument was falsy or non. Non is falsy. Another anti-pattern you see from people coming from C or C++ is things like this. If protocol is HTTP, or protocol is HTTPS, or is MQTT, it's supported. Much more Pythonic to do this, create a set and check for membership in the set. It's much easier to read as well. And Python actually detects this pattern and optimizes for it. It will make a constant set for that. Last one, I have 2 minutes, so let's see if we can get through this. Know why your code is slow and how to make it fast. So there's probably someone in here who works in the oil and gas industry, and they may have at some time in their career encountered a thing called seg-y, which is a file format dating from a long time ago, which stores all seismic reflection data. It's pretty horrible in almost every way you can imagine. Not least the fact that the floating point format is not IEEE, it's some ancient IBM floating point format. So this is a program we worked on to convert IBM format floats in seg-y files into IEEE floats in seg-y files. So we have a program convert sample type, which uses a library we made called segpy. So the first thing to know is that in order to profile a Python program, all you need to do is run it as you normally would and pass -m cprofile and optionally -s, which tells you how you want your output to be sorted. So everyone who's using Python has a Python profiler. You can run it, and you can see here that the total time, which I've sorted by, there are 2 functions at the top there. One is IBM float, and one is convert sample type. They are both using most of the time. They're the functions which are consuming most of the time. But all of the functions at the top of this profile are very tightly related. I've just put the call graph on here. So you can see there are lots of functions working together to do this conversion, and they together are responsible for almost all the time this program is taking. So what can we do about it? Well, I'm going to start by focusing on this convert sample type, which has the _transform function in there. And the main way to make computers go faster is to get them to do less stuff. Right? I mean, you can be smarter about how they do what they do, but it's much better if you can just arrange for them to do less work. So to do this, it's nice to be able to disassemble our Python to figure out what's taking the time back into Python bytecode. And Python also includes a disassembler, which we can just import dis and pass a function to it, and we get the disassembled Python bytecode. And the thing to look at here is you see we have load fast self, and load fast self shows up several times in that disassembly. And that's because in the transform function in yellow on the left there, you can see we're doing several attribute lookups through the self object, through the instance. And that takes time. Loading self is fast, but then searching self, which is a namespace, which is a dictionary, takes time. Yeah, so looking up instance member variables in Python takes time. It's a dictionary lookup, right? So most of the time that's fine. The cost is worth paying. Sometimes the cost is excessive. So I'm going to rewrite this function by not having it as a method. Because just the fact that it's a method makes it quite significantly slower. So I've moved the construction of this method into the dunder_init function here. So now rather than attributes, I can use local variables. I've also specialized the definition of the function. You can see I have if data sample format is some kind of integer, do this, where some range checking is needed. Otherwise, no range check is needed, and we can have a much simpler implementation. So this is a case where I am able to do much less work in certain cases and avoid using local variables. It takes a bit of time to process this code, so if you're interested, I would go back and look at the slides afterwards. But when we've done this, we're only 22% faster. So now we want to go really fast. How do we go really fast? We go really fast by not using Python. Nobody uses Python for performance, right? If you want performance, you use C or C++ or Rust or something that's actually compiled down to run on a real processor. And so if you're particularly interested in this kind of approach, you should go to my colleague Austin Bingham. He's sitting here in the front row. He has a session tomorrow on how to integrate Python and C++. So Austin here did this integration where he took this one function, IBM float, which I will show to you, on left in Python, and he rewrote it in C++. And he told me that he literally took the Python code, pasted it into another file, went through, put some types into it. Then we have to do a bit of work to build some glue so that Python knows how to call this, right? But it's entirely possible. It's very straightforward. When we do this, the program runs 86% faster. So in this whole system, there are probably 10,000 lines of Python, and we can replace 20 of them with C++ and go 86% faster. So that's a very successful approach we've been using to build systems is to build most of them in Python, which is fast. We can write code fast in Python, and then we can write fast code in C++ in the very small parts of the system where performance is actually really important. So I'm a few minutes over time. I'm going to stop here. These are the 7 things. Know when code is executed, know how to use Sentinel objects, know how scopes and namespaces relate, understand the trade-offs for number types, become familiar with some quirks of Python so you are less confused when you get hit by them, understand how to write idiomatic Python, and learn how to use the filer and the disassembler, which are included with Python, and you all have already for free. I'm going to stop there. If you want to know more of this kind of thing, you can come to one of our training courses, or you can buy our books. There are some token URLs at the bottom there, which include these books at a special NDC TechTown reduced price. Thank you very much.